everybody, this is Marian DB from Adelphi University, and today we're exploring relativistic collisionless shocks with simulations. So, relativistic collisionless shocks power some of the universe's most energetic events, such as gamma ray bursts and supernova remnants, and those shocks are mainly made of plasma instabilities. And those plasma instability create magnetic turbulences that end up accelerating particles. And those particles are known to be mainly electrons and ion. And since ions are very heavy particles to accelerate, this research focuses on understanding what mechanism allow those ions to accelerate. So in order to make this possible, we use numerical model to represent what is happening in the universe since we cannot directly observe the plasma in the universe. So we use particle and cell simulation. Using a supercomputer, we have about 200 cells containing diverse amount of particles that we introduce in our much bigger cell. And inside that cell, we allow the particles to enter from the right, and we have a reflecting wall to the left that give us the simulation, the same mechanism as inside those events. So here we can see what we can get as we simulate the shock. We have an upstream region, downstream, and a transition region. And from the image, we can see that the magnetic field are mostly appearing in the upstream region and also merging and growing there. So we focus more on studying the mechanism happening in the upstream region because since that's where the magnetic field are generated, it tells us a lot more about what may cause the particle to accelerate. So we study through what is going on in that region. And so we have been able to test different theories and conclude that it wasn't, for example, a Fermi acceleration that was causing the particle to accelerate. So now what we're trying to do is to figure what creates the magnetic field merging and amplification. And we hope that that will allow us to understand how those particles get accelerated.